a concept in static analysis. The presentation is constructed as follows. First of all, I'll give a short introduction to provide a general view on abstraction. Then we will review soundness and completeness defined in Chapter 1 and walk through their relations with abstraction. Next, we will do some mathematical preparation, prefacing the definitions of abstraction and concretization. Thence, we shall formally define these two concepts. In addition, we will introduce relational and non-relational abstractions with a couple prefatory examples. Abstraction is a concept intends to create machinery which maps elements and their relations from one or saying the original domain to another domain with approximating information of those distant from core properties subject to analysis. Is a framework for approximating the behavior of computer programs or systems of similar complications. Intuitively, since an analyzer virtually cannot obtain every possible outcome of a program, the general goal is to create an over-approximation of the program's behaviors in a way that makes the analysis computationally feasible. The concepts of soundness and completeness were created to describe the informativity of a static analyzer. Embedding these concepts would provide a graceful logic walkthrough, sketching the underlying reason why we wanted to define abstraction and associate the concretization function in such ways. When we see an analyzer sound, a true return value indicates that examined program must satisfy the property of which subjected to the examination. Nevertheless, some programs that satisfies the property might not produce a false outcome. In fact, an analyzer that always returns false is indeed sound but also non-informative. On the other hand, a complete analyzer will always return true whenever the program satisfies the property, assuring that no program will be missed. However, a complete analyzer might produce false true. Similarly, analyzer that always returns true is complete, but also non-informative. If we use a developer reviewer model as an analog, it will be intuitive that we certainly would like the reviewer to be sound, whereas the developer to be complete. Even though the reviewer have misinterpreted the code and subsequently rejected the program, the trade-off is worthy to take because the issue can be easily tempted through communications and the quality of the program is assured. Conversely, we might also consider the preset abstract elements as some sort of high-level requirements, so the developer should try their best to fulfill the requested properties. In short conclusion, an abstraction of a concrete domain should be sound. Next, let's do some mathematical preparation before we head into the formal definition of abstraction and the concretization. An arbitrary relations smaller or equal to on a set X is said to be partially ordering if the following three properties are satisfied. An element X in X should be smaller or equal to itself, namely the reflexivity. For any three elements X, Y, and Z in X, if X is smaller or equal to Y, and Y is smaller or equal to Z, then E should be smaller or equal to Z, or namely the transitivity. Finally, if X is smaller or equal to Y, and Y is smaller or equal to X, then X is basically equal to Y, namely the identity. We shall see that the idea about partial ordering and some other properties of abstraction are closely related to the number theory. An ordering relation defined on a set also responds for differentiating elements in the set. For example, from the real number space, the imaginary number I and minus I cannot be differentiated, since the ordering relation defined over the real number space does not sufficiently describe the complex space. Thus, the nature of a space is actually induced by relations defined on it. Further, since we don't want to go too detailed, let's introduce infimium and supremium. Infimium is basically similar to the minimum element in a number set that is smaller that it is smaller or equal to every other element in the set, whereas for supremium, every other element in the set should be smaller or equal to it. Next, let's do a very straightforward example. So let's say use a power set of the natural number as example. We use a set inclusion or equivalently the subset relation in the set theory as an order relation here. Then together with the power set, we obtain a partial order set. The infimium of this partial order set is an empty set because the empty set is a subset for any other sets, including itself. Similarly, the supremium is a natural number set according to the definition of the power set operation. Now we shall be able to tell why we used the adjective partial to decorate the set. That consider a subset of the power set that only contains 1, and another subset contains 2 and 3. Obviously, the previous set is not a subset of the latter one, neither the latter one a subset of the previous one. So only some elements are comparable in the set according to the defined relation, and that's the reason that we call it partial. On the other hand, if any element in a subset of a partial ordering set has a relation with another element in the same subset, we call such subset a chain. And if a partial order set itself is a chain, we call it a total order set. Obviously, the real number, natural number, integer number set, they are all total order sets. A Galois connection is defined over two partial sets together with two functions that maps elements between those two domains. Consider two functions f and g. The Galois connection is such that for any element a in A and b in B, fa smaller or equal to b if and only if a is smaller or equal to g applied to b. We can see that the Galois connection is closely related to soundness and completeness that we introduced or actually reviewed in the previous sections. So the Galois connection also satisfies the following three properties. The detailed definitions by the monotonicity and Scott continuity and their corresponding proof are given in the handout. If you are interested, please read as your convenience. Now, we are able to formally define abstraction, concretization, and functions that correlate them use the mathematical notations we have described so far. Abstraction and concretization domains are partial order sets with ordering relations defined respectively. Elements and the relations in the two domains are mapped from the concrete domain to the abstract domain using the abstraction function, and from the abstract domain to the concrete domain using the concretization function. As we have climbed that in the previous sections, that we want the abstraction to be sound. When we apply the abstraction function to a concrete element, the result abstract element should describe the original concrete element. On the other hand, when an abstract element is given and we apply the concretization function to it, the result concrete element should be fully described by this element. We can see in the sense of completeness. Consequently, we obtain these relations. In addition, since we want to maximize the informativity of the abstraction and concretization as well, we also further constrain that the abstract element obtained from the abstraction function should be infimum of all elements that describes the concrete element. Similarly, we constrain the concretization function. Combining them together leads to a Gawa connection between the concretization function and the abstraction function. Finally, I would like to introduce relational and the non-relational abstraction. I will walk through some examples as well. First, let's define what is what value abstraction is. Given a value space, the value abstraction is an abstraction of the partial order set defined as a power set of the value space, and the subset as the ordering relation. Consider a function with multiple input parameters. The non-relational abstraction means to treat them separately. So if we had a successfully defined abstraction for each individual, we'll combine them in the sense of set production operation to produce a non-relational abstraction. If and only if every parameter yields like the smaller or equal to relation when mapped to the abstract domain, we use this result as a valid abstract element. Consider the image on the right. If there is another cube in the graph, if and only if the cube is completely submerged by the bigger cube, we name it a valid abstraction. Taking the complex number as an example, like if we're mapping some concrete element to the complex space, since we have known that defining a total ordering is not possible for the complex numbers, but we might still define a partial ordering. We keep the conventional arithmetic ordering for the real part, but make an arbitrary relation for the imaginary part. So for two complex number, a1 plus b1i and a2 plus b2i, if and only if a1 is smaller or equal to a2 and b1 is smaller or equal to b2, we name it a valid abstraction. Let's study one more example. So if the value space, the space is defined as a real number space, we can use a sign and intervals to define the value abstraction. Plus for elements greater or equal to 0, minus for elements smaller or equal to 0. Empty set is obviously the bot, and the row number set is as top. And as of the interval abstractions, we use n0 and n1 to represent two lines on the graph. Values are constraints to the right of the n0 and the left of the n1. For the following two programs, when using a sign abstraction, we cannot differentiate them. But if we use the interval abstraction, we will be able to produce different result. Because for the if we are using sign abstraction, like both program will basically produce a plus. On the other hand, if we're using intervals, the first program will produce 0 to plus infinity, but second program will be 1 to the positive infinity. Nevertheless, high accuracy implies more computational efforts. We should always examine the trade-off, then make the decision. In addition, Relational abstraction is designed to capture relational properties such as x equal to y or x smaller to y. So naturally, a set of equalities and inequalities can be used to represent such relations. Together with a non-relational abstraction, we can extend them from simple intervals, which is signs, to more complicated geometric structures such as polyhedra. Uh, but again, it implies more computational efforts. So, yeah, this summarizes my presentation today. Thanks for listening.